Source: University of Pennsylvania Research, published in Physical Review Letters. Imagine a future where artificial intelligence is no longer powered primarily by electricity flowing through silicon chips, but by particles of light moving at nearly the speed of the universe itself. Scientists at the University of Pennsylvania have now taken a major step toward that future by developing a remarkable new hybrid particle that combines the advantages of both light and matter. Their breakthrough could eventually transform how AI systems process information, dramatically reducing energy consumption while enabling computing speeds far beyond what conventional electronic hardware can achieve. In many ways, this research represents the beginning of a potential shift away from the electronic computing paradigm that has dominated technology since the invention of the first modern computers more than 80 years ago. If you like my videos, subscribe my channel and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. And don't forget to like and share this video with your friends and colleagues. Comments are welcome and open for discussion. Since the 1940s, nearly every computer ever built has relied on electrons. From the earliest room-sized machines like ENIAC to modern smartphones and massive AI supercomputers, electronic circuits have formed the foundation of information processing. Electrons are extremely useful because their electric charge allows scientists and engineers to manipulate them easily using transistors, switches, and logic gates. But as artificial intelligence systems become increasingly powerful and data-hungry, the limitations of electron-based computing are becoming impossible to ignore. Electrons generate heat as they move through materials, and electrical resistance wastes enormous amounts of energy. Modern AI data centers already consume staggering amounts of power, and future generations of AI models could push energy demands to unsustainable levels if entirely new approaches to computing are not developed. This is where light becomes extraordinarily attractive. Photons, the particles that make up light, can travel incredibly fast while carrying information with very little energy loss. Unlike electrons, photons have no electric charge and essentially no rest mass. Because of this, they can move through optical systems with remarkable efficiency. In fact, modern global communications infrastructure already relies heavily on light traveling through fiber optic cables because photons are vastly better than electrons at transporting information over long distances. But there has always been a major problem preventing light from fully replacing electronics inside computers. Photons interact very weakly with their surroundings. While that makes them excellent messengers, it also makes them extremely difficult to use for computation itself. Computing requires more than simply moving information around. A computer must constantly perform switching operations where signals influence and modify one another through logical interactions. Electrons can do this naturally because their electric charge allows them to interact strongly inside circuits. Photons, however, mostly pass through each other without interacting. This weakness has been one of the greatest obstacles preventing fully optical computers from becoming practical. Many experimental photonic AI systems can already use light for certain calculations, but eventually they must convert optical signals back into electronic ones whenever complex switching or nonlinear operations are required. Those repeated conversions between light and electricity slow everything down and consume additional power, reducing many of the advantages photonic computing is supposed to provide. To solve this problem, the Penn research team created an unusual quantum object known as an exciton-polariton. This hybrid quasiparticle emerges when photons become strongly coupled to electrons inside an atomically thin semiconductor material. In simple terms, the particle combines some of the best properties of both light and matter. From photons, it inherits incredible speed and energy efficiency. From electrons and matter, it gains the ability to interact strongly enough to perform switching operations necessary for computation. The result is a system where information can potentially be processed entirely using light-based physics without repeatedly converting signals back into conventional electronics. The experiment itself operated inside nanoscale optical cavities engineered to trap and manipulate light with extraordinary precision. When light entered these tiny structures and interacted with the ultra-thin semiconductor material, exciton-polaritons formed and began exhibiting nonlinear optical behavior suitable for signal switching. The researchers demonstrated what is known as all-optical switching, meaning the system could control and modify light signals using light itself rather than electronic circuits. Most remarkably, the amount of energy required for each switching operation was extraordinarily small, only about 4 quadrillionths of a joule. That energy scale is so tiny that it is vastly below what would be required even to briefly power a microscopic LED. This level of efficiency is critically important because one of the largest challenges facing modern AI is energy consumption. Training advanced AI models now requires enormous computational infrastructure containing thousands of power-hungry processors operating continuously for weeks or months. As AI systems grow larger and more sophisticated, the associated electricity demands continue rising dramatically. If photonic technologies like exciton-polariton computing can be scaled successfully, future AI chips may process vast amounts of information using only a fraction of the energy required by current hardware. That could fundamentally reshape the economics and environmental impact of artificial intelligence. The implications extend beyond energy savings alone. Because photonic systems process optical information directly, future AI chips could potentially analyze visual data from cameras without first converting everything into electronic form. This would allow much faster image recognition, real-time sensing, and advanced machine learning operations with minimal latency. Researchers also believe these hybrid light matter systems may eventually contribute to certain forms of quantum information processing, potentially merging aspects of photonic computing and quantum technologies into entirely new computing architectures. What makes this research especially fascinating is that it represents a convergence of multiple frontiers in modern physics. The experiment combines nanotechnology, quantum materials, photonics, semiconductor engineering, and artificial intelligence into a single platform. Instead of relying purely on conventional electronics, scientists are now engineering entirely new forms of quasiparticles designed specifically for information processing. In essence, they are beginning to redesign the physical foundations of computation itself. Although practical commercial systems are still years away, the proof of concept is extremely significant. It demonstrates that hybrid light matter particles can perform computational tasks using extraordinarily low energy, while preserving the speed advantages of optical systems. Future advances in fabrication, scalability, and device integration could eventually lead to photonic AI accelerators, far more efficient than anything possible with conventional transistor technology. Perhaps most importantly, this breakthrough highlights a deeper transition now occurring in computing science. For decades, progress depended largely on making electronic transistors smaller and faster. But as physical limits approach, researchers are increasingly exploring entirely different physical mechanisms for computation. Instead of simply improving electronics, they are asking a more fundamental question: what if information itself could be processed using completely different particles and physical laws? In that sense, the work at the University of Pennsylvania may represent far more than just a new AI chip design. It may be an early glimpse into a future where computation is no longer dominated by electricity alone, but by engineered quantum systems where light and matter work together to power the next generation of intelligent machines.